pretty much everything is a stochastic process. I'm not just talking about your stock price path or your return series or measures of historic volatility that you're visualizing as a time series, but pretty much everything in this quant finance space is in fact a stochastic process. So you can talk about your portfolio, you can talk about the trading decisions that you're making as some sort of decision process, you can talk about your probabilities of winning and losing trades, you can talk about the expected value of your trading strategy over time. All of these are in fact stochastic processes. Now, why is this such an important idea? Well, I've seen on YouTube and other sources traders who don't have a quant background cite ridiculous things like the central limit theorem or the law of large numbers, and they preach this idea of convergence. If you just follow your trading strategy and your trading strategy is good, then, as you keep flipping the coin, eventually it's going to converge to that expected value and you're going to accumulate that positive expected value over time. That's simply not how this space works. That's why we study these processes. That's why we have pricing models. If it were that simple, then we wouldn't need any processes in general. We could just model them as random variables with fixed distributions. But in fact, that's not how any of this stuff evolves through time. So motivating this video and the need to understand stochastic processes and simulating stochastic processes, not just from a modeling standpoint, but also as a necessary standpoint to understand the space, I want to talk today about the Karhunen law of expansion of the Brownian bridge. We're going to talk about the solution in continuous time. We'll talk about the discrete time solution as well. We'll go about discretizing these solutions for simulation. I'll show you the Gaussian cookbook where you can go about interacting with these simulations on your own. And then we'll close out the video and talk about some future topics and implications in pricing. Now that we have motivation to study these processes and understand this theorem, let's set up the space and then we'll talk about the application of the theorem. So for starters, we're going to say that we have a stochastic process x sub t in this L2 probability space. So we have some sort of sample space. We have a sigma algebra and a probability measure. And all we're saying here is if it's in this L2 space, that x sub t is square integrable. That's just what this L2 probability space is, the set of all processes that are in fact square integrable. It's a Hilbert space, but that's not the point of this video here. We're just going to say that this pretty much just means that if we take the expected value of x sub t squared, we get something that is finite. And this is equivalent to suggesting that the covariance function for all s and t in our interval of interest, we'll say from A to B, is also going to be finite. Okay, so that's not too bad. That's just simply suggesting that it is square integrable, the stochastic process. For the purpose of this video, we're also going to consider that the expected value of this process is just going to be mean 0. And we will also say, unsurprisingly, that k sub x s sub t is going to be this covariance function. So it's going to be the expected value of x sub t times x sub s. And this is just the definition of covariance. Of course, because we have mean 0, it's just going to be the product of these two variables at the indices s and t. So what's the purpose of this theorem? Well, the purpose is to decompose the process x sub t into an infinite series of the product between a Gaussian vector and its eigenvalues and eigenfunctions. So what does this look like? We're saying if we apply this theorem, we should be able to find a representation of x sub t, which is equal to this infinite series from k is equal to 1 of this Gaussian z sub k multiplied by an eigenfunction evaluated at the time t. So this decomposition here might be a little confusing because we don't see any eigenvalues being represented here. In fact, we could generate z sub k in one of two ways. We can generate z sub k using the eigenvalues that we solve for, or we could generate a standard normal and then scale this series by the square root of the eigenvalues. So essentially what I'm saying is in this representation, we're saying that z sub k is distributed by a normal distribution, mean 0, with a variance of the corresponding eigenvalue. Now this is equivalent, this representation here, is equivalent to the representation here where we say x sub t is equal to this infinite series representation. But now we're multiplying by the square root of the eigenvalue along with the eigenfunction, and we're saying that z sub k is just going to be a plain old standard normal random variable. So these two are in fact equal, and they're saying the same thing. The only difference is whether or not we're going to generate that Gaussian vector using the eigenvalues as the variance, or if we're going to scale the entire representation by the square root of the eigenvalues, which is going to yield the Gaussian vector with that variance in any case. I'm hoping this isn't too hard to see. Another way to look at this is if we have z sub k distributed as a standard normal Gaussian, and we just take z sub k multiplied by the square root of the eigenvalue, then we take the variance of this quantity, then this would be equivalent to, this is a constant, so we take it out and square it. Then we have lambda k, and we're left with the variance of z sub k. And the variance of z sub k in this case is just going to be 1, so we're left with lambda k. That's how we end up with the correct variance structure in this instance. And of course, the other way to do this is just by plugging in lambda k directly into this representation. Then if we were to just take the variance of z sub k, we would just simply get lambda k. So that's why these two representations are equivalent. But this is essentially the decomposition that we are after. So how do we find these eigenfunctions, the eigenvalues? Well, we have to set up and solve this integral eigenvalue problem. And this integral eigenvalue problem is going to be the integral over some sort of region a to b of the covariance function as a product with the eigenfunctions integrated over that region. And we're setting up this integral to be equivalent to the eigenvalues multiplied by the eigenfunctions. So this is the integral eigenvalue problem. And in this case, what we're going to do is we are going to set up our region a to b. We'll just select a unit region 0 to 1. And we're going to go about solving this integral eigenvalue problem for the eigenfunctions. And then we can go about solving for the eigenvalues, and we can arrive at this decomposition here, this infinite series decomposition. Now, of course, this is continuous time. And if we want to discretize the continuous time solution, we certainly can, but we're going to have to truncate this infinite series representation. And the accuracy of our discretization is going to depend on the spectral decay of this eigendecomposition. So really what I'm suggesting is, depending on where the variance cuts off in this series of eigenvalues, we're going to need more or less terms for a more accurate representation. Obviously, in a computational setting, we can't have an infinite number of terms, so we're going to have to truncate at maybe 500, and hopefully that is sufficient. Of course, you're also subject to accuracy errors if you're trying to measure some sort of covariance empirically with the granularity of some sort of time step, along with the number of sample paths. But this will be more clear when we get to the simulation portion. I just wanted to touch on this, that this is a continuous time representation, and we don't have the capacity to simulate anything to infinity. So we're going to need to truncate when we go about simulating and discretizing this solution. Moreover, if we wanted to just operate in discrete time, we certainly could. And really, this problem is analogous to just a classic matrix decomposition. So the discrete time version of this problem, if you will, is much easier, I'll say, with air quotes, in that we just have the covariance matrix and we need to diagonalize the covariance matrix, and that's easily done via eigendecomposition. So really, in the continuous time sense, I'm going to create kind of like a little chart here of continuous time. I'll change the color, make it green. Continuous time. And then discrete time. So here's kind of the analogy of the structures we're dealing with. So in continuous time, we have this covariance function. And in discrete time, we typically just deal with this covariance matrix. The integral eigenvalue problem this is really just the matrix diagonalization problem. So this is just going to be an eigendecomposition of that covariance matrix. And the infinite series representation, so this x sub t is equal to the infinite series of the Gaussian. We'll say that this is standard normal. So we'll have the square root of the eigenvalues as well, multiplied by the eigenfunctions. This is analogous to, let's say we have this decomposition in discrete time. X sub t is equal to q lambda to the 1/2 times z sub t, where z sub t is just this standard normal Gaussian. So this is the continuous to discrete time analogy. So essentially what I'm saying here is we have this covariance function. In discrete time, we have the covariance matrix. So continuous time, covariance function, discrete time, covariance matrix. We have this integral eigenvalue problem in continuous time. In discrete time, we have this matrix diagonalization problem. And in continuous time, when we get the solution to this integral eigenvalue problem, we arrive at this infinite series, this decomposition of the process. And of course, you're going to have to truncate when you discretize to simulate, say, sample paths. But in the discrete time sense, it's a lot easier, and it's probably a lot easier to even see why this decomposition works, because we're trying to simulate this process with a desired covariance structure, for example. And all we're doing is we're taking a standard Gaussian, and we are maintaining the direction preserved by the eigenvectors, and we are scaling by the variance captured according to the eigenvalues. And that's pretty much what's happening in continuous time too. It's just the discrete time analog. So, one pretty simple way to look at why this works is to look at just the covariance of the discrete time decomposition. So if I was to take the covariance of x sub t, then I know that this is the decomposition, so I can just represent x sub t as q lambda 1/2 z sub t. And now this is just taking the covariance, which is quite easy. All I got to do is take q out, take lambda to the 1/2 out, and then I have the covariance of z. And then I have lambda to the 1/2. You can transpose it, but it's a diagonal matrix. And then I have q transpose, but the covariance of z sub t is I, right? It's just standard normal vector. So I have q lambda to the 1/2, lambda to the 1/2 qt. Okay, this just turns into q lambda qt, but this is just the eigendecomposition. So we end up with the original covariance matrix gamma. And that is the covariance structure of the process that we were after anyway. So that's why this decomposition works. We could go through the continuous time proof, but I'd rather start by setting up and solving this integral eigenvalue problem in continuous time, because I don't think it's as intuitive as just looking at this in discrete time. It's very similar in structure, what we've just gone over here, but we're going to move now to setting up this integral eigenvalue problem for the Brownian bridge. We'll define Brownian motion, define the Brownian bridge, and then we'll set up and solve this problem. Let's start by defining Brownian motion, then we'll talk about the Brownian bridge, and we'll set up this problem and solve it. So the Brownian motion is characterized by A, at time 0, the Brownian motion is 0. B, the Brownian motion is almost surely continuous. C, the increments of Brownian motion are independent. And D, the increments of Brownian motion are distributed normally with a mean of 0 and a variance of the time step. And this is going to be for all relevant indices. And this shouldn't be too much of a surprise because Brownian motion really is just classified as this idea of, if we have randomness over time, then the increment from 0 to 1 is going to be much less. So the variance is much less than the increment from 0 to 100. So essentially what we're doing is, if we look at the increment from 0 to 1 of the Brownian motion, we're drawing from this normal distribution with a mean 0 and a variance of 1. So once we make that draw, we're going to have a point in space, right? So it's just a standard normal distribution from 0 to 1. But what if we stepped out to 100, right? Then the increment from 0 to 100 would be distributed normally. So we would have another normal distribution for that entire jump, but with a variance of 100. So you're going to have a much wider range of possible points, for example, out at 100 than you would at, say, 1. And that makes sense, right? Because that's the uncertainty over time. And then you're going to accumulate all of those increments, and that's going to be your Brownian motion. You'll have all these paths, and the variance is going to increase as time continues to march on. If that's the Brownian motion, now let's talk about the Brownian bridge. So the Brownian bridge is defined as B sub t, where we have a classic Brownian motion such that at time cap t, we are back at the origin 0. Another way of defining this is saying that B sub t is equal to W sub t less t over cap t, W sub cap t. So we're always going to be accumulating towards that end point, that end anchor point, W cap t equals 0. What does this look like graphically? Well, graphically, kind of looks like a bridge. So we have time cap t, we have our origin here, and we are going to be generating paths all the way out to cap t, and we're going to be back at that anchor point 0. So at time cap t, our W sub cap t for every single process is going to yield 0. So if we generate another path, maybe we have a path that looks like this. It's going to end up right here. Another path here, another path here, another path here. So one way that you could use this hypothetically is, let's say that you have some sort of price at night. So at close, you have some sort of stock price, and at open, you have another price. So let's say we start here and then we jump up to here. You could use a piecewise linear interpolation of the prices. So this is, let's say, 4 p.m. and this is 9:30 a.m. There's like a little jump. You could model it as a jump, or you could also model it as some sort of bridge process where there is a lot of randomness between those 2 points. Hypothetically, you could do something like this. So this is the Brownian bridge. This is how the Brownian bridge is classified. Now, let's see how we can use the Karhunen law of expansion to decompose this process B sub t for simulation. There's a pretty simple recipe we can follow to go about solving for this continuous time decomposition. That is, number 1, define a valid process x sub t, in this case B sub t, our Brownian bridge is in fact a valid process. Step 2 is going to be to determine the covariance kernel. And that's just our covariance function, which for the Brownian bridge is quite well defined as the min of S and t. So that's the Brownian motion component. And the bridge component is just going to be less this product of s and t, normalized by the time 0 to cap t. Step 3 is going to be to establish and solve the integral eigenvalue problem. Step 4, solve the integral eigenvalue problem. Step 5, which is optional, is we can normalize. So we can normalize the eigenfunctions such that they are orthonormal with respect to the L2 inner product. And all that is suggesting is that the integral over our selected region of our eigenfunction squared is going to be equal to 1. And then step 6 is just going to be to define the decomposed process. And in this case, we are going to be able to define it as x sub t is equal to this infinite series representation of a Gaussian multiplied by the square root of the eigenvalues for the respective eigenfunction all the way out to infinity. So these are the steps. This is the general, I'll call this the general recipe in continuous time for decomposing such a process using the Karhunen theorem. Let's go about actually doing and solving for this integral eigenvalue problem to find this decomposition now. So let's move on to a new page and let's go through this for the Brownian bridge. Step 1, we're well defined. B sub t. Check. Step 2, we know the covariance kernel. Boom, check. This is the easy part. We just need to set up the process that we are going to decompose, and to do that we need the covariance structure. We need the process. So we've defined the Brownian bridge. We know that the covariance structure is well defined. We could call this k sub b if we'd like to be more specific. I think here I called it k sub x, so this should be probably k sub b. Come on down here. Step 3. We got to establish this integral eigenvalue problem. So if you recall, the integral eigenvalue problem is the integral from a to b, k sub x sub st of e sub k s ds is equal to lambda sub k e sub k t. So we have our eigenvalues, our eigenfunctions, and we have this integral eigenvalue problem here. And we need to pick a region now. I'll just pick the unit region. So I will say that a is going to be 0, b is going to be equal to 1. So this implies that cap t is also going to be equal to 1. So if we set up this integral eigenvalue problem, we are going to get the integral from 0 to 1 of the covariance function, which is going to be the min of s and t, less s over t, or less s times t over cap t, times the eigenfunction, integrated over that region, and this is going to be equivalent to the eigenvalue scaling the corresponding eigenfunction. This is certainly a beast. Let's go about tackling it step by step. I want to be as explicit as possible in each step of the solution. So for starters, we have to deal with this min function. We're going to break up this integral into the sum of two smaller integrals, where in one case we have an s component and in the other a t component. So what do I mean? The min function is just a piecewise function that's going to choose s or t depending on whether or not t or s is smaller. So if this is the case, then what I'm going to do is I'm just going to break up this integral from 0 to 1 into two regions. I'm going to have a region where t is smaller, and a region where s is smaller. So we're going to go from t to 1, we're going to go from 0 to t, and in this case, s will be smaller, and in this case, t will be smaller. So if we apply the min function to these regions, so we have this region 0 to t, the min is going to be s. And then t to 1, if we apply this min, then we are going to get t. This is equivalent to breaking up an integral into two smaller integrals where you just have two disjoint components of the domain that you're integrating over. So what does that look like graphically? Pretty much what we're doing is we're saying if I have some function here, let's call this f of x, and I'm integrating this function from, let's say, 0 to 5, then the integral from 0 to 5 of f of x dx is going to be this shaded region. But this is equivalent to the integral from 0 to 3 plus the integral from 3 to 5. So if I have this region here, this red shaded region, and this purple shaded region, I can sum the red and purple region to get the blue region, the original blue region. That is exactly what we're doing by breaking up the integral into two components, s and t. So let's write that out. This will break up into the integral from 0 to t. This is the s component. And we also have to consider the corresponding eigenfunction. So e sub k s ds. Now we also need to consider the other region from t to 1. And this is going to be the t component. We consider that eigenfunction as well. Now we need to also subtract out the second component to that covariance kernel for the Brownian bridge, and that's this product of s and little t normalized by cap t. Remember, cap t is spoken for, right? So we have this region from 0 to 1, so a is 0, b is 1. That means that cap t, or terminal time, is also going to be 1. So we can actually discard that term altogether, subtract out the integral from 0 to 1 of st eks ds. This is equivalent to the eigenvalue scaling the corresponding eigenfunction. Now let's go about establishing an ordinary differential equation that we can then use to solve for the eigenfunctions and corresponding eigenvalues. To start, we're going to differentiate both sides with respect to little t. So I'm going to have d dt of both sides of the equation, and we are going to differentiate each one of these integrals individually so they make more sense. So for starters, we have d dt of this integral from 0 to little t of s times the eigenfunction. And that's this first integral here that we're going to be looking at. Now, when you differentiate an integral that has only a variable limit, so what I mean is you don't see t anywhere else in this integral besides the limit of integration. All you have to do is evaluate the integrand at that limit of integration. So the integrand is just this functional component here, and I'm going to plug in that limit of integration t everywhere I see a variable in that integrand, and then I'm done. So this is just going to be equal to t, the eigenfunction evaluated at t. There's no other t in this integral expression, so that's going to be the derivative. So we are effectively done with this first integral. Now we're going to look at the second integral, and we're going to have d dt of this integral from t to 1 of t times the eigenfunction. And here you'll notice that we have another t term. So what I said for the first integral still holds, but now we have to apply the product rule, because I can take this t out of the integral because it's not an integral with respect to t, it's an integral with respect to s. Now I can just differentiate like normally and treat these as two separate functions. Essentially, this is a g of x, and this little t is an f of x. So I can apply the product rule to f and g, and this is going to be equal to, if we take the derivative of t, so I'll call this my f, I'll call this integral my g, then we need f prime times g plus g prime times f. So what is f prime? Well, f prime is 1. We take the derivative of t with respect to t, we get 1. And then g is just going to be the integral component. Now we need to take the derivative of g. Well, I just said in this first representation here, if the only variable that we are differentiating an integral with respect to is in its limit of integration, then we just evaluate the integrand at that limit of integration. So we're going to add this g prime component, and the g prime component is just going to be negative e sub k evaluated at t in that lower limit of integration. Now we just need to multiply by f, which is that original t. So this is just the product rule being applied to two functions, f and g. The only thing is the function g is just an integral with a variable limit. So this is going to be the derivative of the second integral. Now the third integral is actually much easier. It's going to be d dt, the integral from 0 to 1 of st. Then we have our eigenfunction. And when we differentiate this, you'll notice we can just take this t out. And there's no other t variable in the integral, so we can just get rid of the t and call it 0 to 1 of s times the eigenfunction. So these are our three solutions, 1, 2, 3 to differentiation. And differentiating this side of the equation is just very easy because lambda k is a constant, and e sub k, just take the derivative with respect to t to set up this differential equation. So now we can glue all these pieces together. So we get, if you notice here, we get t times our eigenfunction, and then we have minus t times our eigenfunction. So these will actually cancel out. Then we can sum the remaining components. So we get the integral from t to 1 of that eigenfunction plus the integral from 0 to 1 as the eigenfunction is equal to lambda sub k e prime of t. Terrific. So that's after differentiating once. Now let's just differentiate again. So I'm going to apply this derivative again. And we get the same situation here. We just have a variable in the limit of integration, so we'll just substitute t into the integrand, and we'll get e sub k evaluated at t. If we differentiate this integral with respect to t, well, there's no t. So this goes away. And then we just differentiate this side again, and we have a second derivative of our eigenfunction. So this is equivalent to, this is negative because it's the lower limit, negative e sub k of t, which is equal to lambda sub k e prime prime of t. And this is going to be our ODE to solve. What is the characteristic equation of this second order differential equation? Well, we're going to have lambda k r squared minus 0 r minus, or I should say plus 1, is equal to 0. That is the characteristic equation. Does not take a rocket scientist to see that we end up with r squared is equal to negative 1 divided by lambda k. And unfortunately, when we take the square root of both sides of this equation here, we are going to get that r is equal to, we have plus or minus the square root of 1, I should say negative 1, over lambda k. So we are dealing with a complex root to this characteristic equation. this is going to imply that the general solution of this differential equation is going to take the form of e sub k is equal to a sine of t divided by square root of lambda k plus b times cosine of t divided by the square root of lambda k. And I'm just getting the square root of lambda k from this original term here. Keep in mind that you're just taking the complex component and you are multiplying that coefficient by the original functional t. So it's going to be t scaled by this eigenvalue, this corresponding eigenvalue for this eigenfunction. And the other component of this complex number is just going to be 0. So there's no real component, right? This is just an imaginary component. So really a is actually supposed to be c1 e to the lambda t, and b is supposed to be c2 e to the lambda t. But lambda is the real component of the characteristic equation's roots, and there is no real component, so it's 0. But e to the 0 is 1, so we're just going to be removing this exponential term, and we're going to be left with some arbitrary constants c1 and c2, which I'm just calling here a and b, and likely you'll see it written as a and b instead of the product of these two when you don't have the real component. So our general solution is going to be given by a sine t over square root of lambda k plus b cosine t square root of lambda k. And again, this is just saying, hey, you just multiply the function value, evaluating the eigenfunction at t, multiply that by the corresponding imaginary component of the characteristic equation's root. And that's how we get this t over root lambda k. That's coming directly from this characteristic equation. We can now start to look toward the boundary conditions, and we can just take the original formulation of this integral eigenvalue problem, and we can evaluate it at the boundary 0. So I'm just going to copy this, bring it on down here, and I'm going to be looking at where t is equal to 0. So I'm just going to plug in 0 everywhere I see a t. And the integral from 0 to 0 is 0. Anything multiplied by 0 is 0. So all I get is 0 is equal to lambda k multiplied by the corresponding eigenfunction, but it's equal to 0, so scaling is arbitrary. I can get rid of it, and this is going to imply that the eigenfunction evaluated at 0 is 0. So I can use this now in the general solution. The e sub k of t is equal to a sine of t over root lambda k plus b cosine of t over root lambda k. If this is true, then when I plug in 0 here, I should get 0. So I'm going to get e sub k 0 is equal to a sine of 0 plus b cosine of 0. Sine of 0 is just going to be what? Sine of 0 is 0, right? But cosine of 0 is 1. So this is going to imply that e sub k of 0 is equal to b. But that can't be the case, it has to be equal to 0. So what does that mean? It means b must be 0. B must be 0. So using this first condition, we find that b must be 0, and we're left with e sub k of 0 is equal to a sine, I'm sorry, not of 0, of t. This is our new general equation. Okay. We still need to figure out lambda k, and we still need to figure out a. So let's now look to the condition for 1. Can take this original representation too. I'll just copy it again. Or I still have it on my clipboard. I should be able to paste it. Cool. And let's look at the case where t is equal to 1. 0 to 1, 1 to 1. That's 1. Well, the integral from 1 to 1 is just going to be 0. There's no mass to integrate in that region. And check this out. If we take a look at these two integrals, they're equivalent. Because t here is 1, we have 0 to 1 and 0 to 1. So we're subtracting the same integral quantity. So we just end up with what? We end up with, and this is at t is equal to 1. We end up with 0 is equal to lambda k e sub k of 1. And again, scaling is arbitrary, so we just get that e sub k of 1 must in fact be 0 from our second boundary. Cool. Let's take our general equation and see what we can do. So e sub k of 1 must equal 0. Let's plug in 1. Okay, but this has to equal 0. All right, interesting. Now, trivially, we could say a is equal to 0, but that's not going to be the case, because the eigenfunction is not trivially 0. It's non-zero. That's the purpose of using these eigenfunctions. So what do we do here? Well, we need to figure out where the function sine can be 0 in this case. This is where we can go about solving for our eigenvalues. So really what we need to ask ourselves is, since a can't be 0, otherwise the eigenfunction is just going to be 0. That's not the definition of, it's a non-zero function by definition. So we need to figure out what these eigenvalues are to make sine 0. So where is sine going to be 0? Well, if we remember from good old pre-calculus, sine is going to be 0 only at multiples of pi. So this is going to be 0 pi or 2 pi. This is going to be pi. Sine will be non-zero elsewhere. So what we need to do is we need to figure out what lambda is such that we get some sort of multiple of pi. So really we're just saying that we have 1 over root lambda k is equal to k pi. And if we solve for this, then we're going to multiply over, we get lambda k is equal to 1 over k pi squared. And these are our corresponding eigenvalues. So in other words, the only way that this can be true, the only way that we can have this condition be true such that the eigenfunction is not trivially 0 is with eigenvalues for the corresponding eigenfunction equivalent to 1 over k pi squared, where again k is this indexing of arbitrary eigenfunctions and eigenvalues and their corresponding eigenvalues. So that's going to leave us with this solution. We're going to get E sub k of t is equivalent to a sine of 1 divided by the square root of lambda k, which in this case is going to be equal to 1 divided by k pi squared. We can take the square root of both and then flip it, and we end up with a sine of k pi. Oop, that's a t, not a 1. T. Fantastic. So this is going to be our solution here. And now we can normalize if we like. And we can normalize with respect to the L2 inner product, such that the integral from 0 to 1, so this region of the eigenfunctions squared, is equivalent to 1. And this just implies that we have the integral from 0 to 1 of a squared sine squared k pi t, or I should say s ds equal to 1. And we can take that a squared out. We can use the fact that sine squared x is equal to 1 minus cosine of 2x divided by 2, a classic trig identity. So this is going to be equal to then the integral from 0 to 1 of the 1 minus cosine of 2 pi ks divided by 2 ds. Set this equal to 1. And then here we can just solve this for a. And this integral looks far worse than it actually is. You actually just end up with this. This goes to 0. This component goes to 0. And you're just left with this integral. So you have a squared, the integral from 0 to 1 of 1/2 ds minus the integral from 0 to 1 of cosine of 2 pi ks divided by 2. But in this case, right, we're just doing multiples of 2 pi. So we're going to end up with just 0 if we try to integrate cosine in this fashion. Really, we're just integrating from above the x-axis and below the x-axis. So they're just going to cancel out. We're going to end up with 0 in both cases. So that's just going to yield, it's going to yield nothing. Actually, it's not even, yeah, since it's cyclical, it's just going to yield nothing. So then we get a squared of 1/2 minus 0, because this is 0, is equal to 1. And that's just going to imply that a is equal to the square root of 2. Wonderful. Now that we've normalized the eigenfunctions to be orthonormal with respect to that inner product, we can write the solution as ekt equal to root t of, then we have sine of k pi t. Awesome. It feels like we may have forgotten the plot, but I promise that's not the case. We are defining the Brownian bridge in terms of the infinite series of its eigenfunctions scaled by its corresponding eigenvalues multiplied by a Gaussian vector. And in this case, we have now that bt, this stochastic process, is equal to the square root of 2 times this infinite series of a Gaussian. And in this case, we are going to just be looking at the standard normal Gaussian, so that we can multiply by the corresponding eigenvalues, which, if you recall, the eigenvalues is going to be, the eigenvalues are going to be 1 divided by k pi squared. However, we do not want to multiply by the eigenvalues because we want the Gaussian to have a variance of what? A variance of the eigenvalue for the corresponding eigenfunction, not a variance of the square of the eigenvalue. So we need to take the square root of this, and we end up with 1 over k pi. So we're going to scale this by 1 over k pi, and then we have our eigenfunction, which is sine of k pi t. And this is going to be the Karhunen-Loève expansion of the Brownian bridge. So in conclusion, the continuous time solution to this integral eigenvalue problem is just this infinite series of a Gaussian multiplied by the corresponding eigenfunction and eigenvalue. Index k is equal to 1 to infinity, scaled by the square root of the eigenvalue, and z sub k is going to be our standard normal. And that is the solution to the integral eigenvalue problem. Now, it shouldn't come as too much of a surprise that many stochastic processes will not have a continuous time solution. We were very fortunate in that many of the necessary terms canceled out. A lot of those integrals will become intractable, and we won't be able to establish an ordinary differential equation or a second order differential equation that is solvable in any capacity. So we have a discrete time solution in this context as well. But what I've done here is I've gone to the Gaussian cookbook. This is just a passion project for Gaussian process enthusiasts like myself, where I have a list of recipes for simulating processes from these different types of decompositions and expansions and relevant articles and resources. So what I've done here is I've created one for the Brownian bridge, and you'll notice that this is the expansion that we have just solved for, and it outlines the general recipe. Of course, it doesn't walk through quite yet each of the steps. I will have to go back in and implement that. But this is going to be the discretization of that continuous time process. So in Python, what we've done here is we've represented this expansion in terms of a certain number of steps between 0 and 1. We've represented a certain number of terms in the spectral decomposition. So that is the k, how many eigenvalues are we using? And we've also taken a look at the number of paths that we can generate to match the empirical covariance to the theoretical covariance structure. So this is the discretization. And in the continuous time sense, error comes from the truncation of the spectral decomposition along with the number of paths that have been simulated, along with the granularity of the process. Now, that's a lot of words. Let's go to the simulation because that's where the cool stuff is. So here, this is the Brownian bridge. I have the continuous time discretization here. And what you'll see is we're only using 50 terms, and we have 5 sample paths. This is the theoretical covariance. This is the empirical covariance. So what happens when we increase the number of terms and we increase the number of sample paths? Well, we're going to converge by the law of large numbers, assuming we are sampling from the correct distribution, to the theoretical covariance structure. And that's exactly what will happen. I just don't have the capacity to simulate enough paths computationally in this very simple GitHub pages hosted website. But this is the discretization of the continuous time solution. Now, just as we said before, we can do it in discrete time as well. Now, I said that many processes won't have a continuous time solution. That's true. So if we look in discrete time, what we're going to have here is we're just going to do the exact same thing we just did, but numerically. And instead of solving this integral eigenvalue problem analytically like we just did painfully line by line, we can just establish this covariance matrix because the covariance matrix is very well defined. We know the covariance structure that we're after for many of the processes that we desire to simulate. So all we have to do is establish this covariance matrix, diagonalize it, construct a Gaussian vector, and take the product. That's so much easier. That's significantly easier. So all I've done here is I've implemented the discretization of the Brownian bridge. So it's a discrete time version of the Karhunen-Loève expansion in some sense. But you know what we've done here now in this simulation is it's not for a discretization of a continuous time solution, it's the discrete time solution. So what we're doing is we're implementing this solution for discrete time. We have a fixed interval that we're looking to generate these paths for. And that's exactly what we're doing in the discrete sense. So what I can do is I can change it from the continuous sense to the discrete sense. And this is now what we're looking to do. We're looking to discretize this. Actually, this equation's wrong. I have to go back in and change it. What we're doing is we are looking to compute this eigendecomposition and construct this process by dotting the eigenvectors and eigenvalues with a Gaussian vector. So when we do that, we're going to end up with time steps and sample paths, but we don't have this expansion term to truncate. So in terms of the spectral decomposition, we're not truncating an infinite series to some sort of finite discretization. We're literally discretizing the solution in the sense that like we have the total number of time steps that we're after, and we're just trying to simulate the density for those time steps. We're not trying to take this continuous time solution and discretize it. So they're two sides of similar coins, but they're not precisely the same. I certainly encourage the viewer who is interested in more of a formal write-up of this theory in the context of Brownian motion and the Brownian bridge in a continuous time and a discrete time setting to check out this note that I've written on recipes for simulating stochastic processes. So what I've done here is I've outlined this Karhunen and Loève theorem along with some intuition and general recipes for continuous and discrete time processes, and I've applied it to the Brownian motion. I've also applied it to the Brownian bridge, and I show that you can essentially converge to the theoretical covariance structures applying these general recipes. They're just useful discretizations for either the continuous time solutions or the discrete time solutions. So what are the implications of this in finance and pricing? Well, if you can't simulate your stochastic processes correctly, then you're not going to be quoting prices correctly based on your model and its assumptions, and you may exhibit arbitrage, you may exhibit a whole mess of issues, undervaluing, overvaluing different components of your price, so on and so forth. So it's very important to understand this foundational theory, because if I can't simulate a stochastic process correctly, and keep in mind, many of the models that we choose to use will not have analytically tractable solutions in continuous time. So we're going to resort to numerical techniques like Monte Carlo simulation to generate our prices. But if we can't simulate these processes correctly, decompose them and simulate them correctly, then how could we ever hope to quote accurate prices? We don't want to offer prices that are inaccurate or over and undervalue different components of the contract, or even offer arbitrage. That would be an absolute mess. So our models in the finance sense need to be consistent. We need to ensure that we're stating as little about the true distribution as possible, and again, so on and so forth. That is just the purpose of all of this study in stochastic processes. Is if we can't simulate a Brownian bridge, if we can't understand the continuous time and the discrete time solutions in the context of the expansion or the diagonalization of a covariance matrix in the discrete sense, then how are we ever going to hope to simulate, say, a Volterra process for our rough Bergomi model? We certainly need this foundational theory in order to be able to extend to more complicated models that may be able to capture better intricacies or fit more complicated empirical things, like maybe we have a joint calibration problem and things like that. If we can't understand it with a simple Brownian bridge, we certainly won't be able to understand it in the more complicated sense, especially when speed and accuracy and all of those things start to matter as well. With that, I hope you enjoyed this video. I hope you learned something. I know this was a very long and technical video, but if you enjoyed it, please leave a like, subscribe, leave a comment. Let me know if you want more content like this in the future. If we want to talk about very technical aspects of the quant finance space, then this is what it looks like. And this is quite an elementary solution to something that is very well defined. So we're really just scratching the surface here. We haven't brought in a large variety of techniques available to us, from Fourier transforms to different discretization schemes. So let me know if that's something you'd like to see more of in the future. Other than that, thank you again so much for watching, and I will see you in the next video.